Okay, I think it's time to get started. Thank you everyone for joining us. My name is Matt Radishonsky. I'm a member of the Mentor Graphics Embedded Software team, and I'll be facilitating this hangout with Stan Shebs today. We are very excited about this event. It's our second Google Plus Hangout, and we've got some more planned for the future. We'd like this to be as interactive as possible, so please feel free to use the chat and comment section below the live video YouTube stream that you've got on this event page here. We'll be answering these questions real time in our Google Hangout, which will play on this video stream. We've got also some Q&A time allocated for the end of this presentation, so if you'd like to save your question for the end, that's fine too. So I think we're ready to go. So joining me today to talk about best practices for debugging embedded software is Stan Shebs. Stan manages our debugger team for the Mentor Graphics Embedded Software Division. He's been a maintainer of the GNU Debugger GDB since 1994 with Cygnus Solutions, and then at Apple, and then at CodeSourcery prior to Mentor Graphics. Stan's focused on support and worked on every phase of the development process, from architecture simulator and bring-ups of first silicon to squeezing out maximum performance from a mature system. So now I'll pass the presentation over to Stan, and once again we'd like this to be as interactive as possible, so please feel free to use the chat and comment section below the video stream there. And then following this presentation, a recorded version of this live YouTube stream will be pasted on this page, so you'll be able to go back and watch it, and we'll address any Q&A questions that we didn't get to in the presentation also. And then we'll also post a link to Stan's slides. So without further ado, thanks again for joining us. I'd like to welcome Stan Shebs. So Stan, I'll turn it over to you and turn off my microphone.
All right. Thanks, Matt, for the introduction. As he suggests there, I've been a tools developer for a long time. Ironically, haven't actually done a whole lot of operational embedded systems debugging on my own, but I have supported quite a few developers over the years, sending an email, even a couple cases paper mail, if anybody remembers that, with their problems. And so a lot of what I've done is to try and figure out, what's going wrong with their systems. And so, so anyway, what I'm going to talk about today is essentially a distillation of some of that. And it's not going to be so much about the business of using the tools, because you can read the manual and poke around with them and so forth, but it's really going to be more about the technique. That is, things that work well, things that don't work well, things to watch out for. So I'll have a few slides here, and I'll pop up on the screen share and started with those. Okay, so and what is it that's so special about embedded? First, we have limited input-output options. The classic embedded system model is you have an analog voltage pin going in and you have one LED going out. A lot of real systems have more than that, but still, it's really all about the limited computing resource. Your CPU is going to be smaller, you're not going to have so much memory available, it's not going to be as high as speed. You have hardware access, and hardware means timing sensitivity, means you can actually break and burn out your hardware if things go really wrong. And the more likely cases, you just end up with general catatonia. The system is not communicating and you can't tell why. And of course, there's real-time behavior. You have response deadlines, how quickly you react to a button press. And then you have dynamic control algorithms whose behavior is very much dependent on a real-time stream of input data in order to compute the right results. So first off, I'm going to talk a little bit about the general principles. And these are principles that apply to all kinds of debugging, but there's aspects to them that are more intensified, shall we say, for embedded systems. So an example is the stop and think, identify the actual bug, question your assumptions, notice details, and then go for the insight but verify it. What do we mean by stop and think? Debugging is a problem-solving activity. You have to state the problem, form a hypothesis, gather evidence for and against your hypothesis. If the hypothesis in fact turns out to be the solution based on your experimentation and testing, then you're done. If not, you have to go around again, form a new hypothesis, start all over. So it's a very intense thinking kind of process. It's something that's not easily automated. There's some actually interesting similarities of forensics for people who've seen crime shows, CSI, Law and Order, that sort of thing. They're actually kind of interesting to watch with a computer scientist's eye and see how the solving process is very much like program debugging. Your bug is the criminal, the modules are your various suspects, and then the nice part is you get to be the good guys. So, but they go through the same kind of process. There's they form a hypothesis, pick out a suspect to question, doesn't pan out, have to go try a different suspect, and so forth. And so there's a lot of interest in seeing how that process works in a different area. So first of all, you have to state the problem. Stating the problem, and key thing here is to state the problem as the observed symptom, not as an initial hypothesis. And so you want to watch out for assumptions that you might be jumping into that are not actually borne out by the facts yet. So let's take an example. Suppose the screen on your little display device is all yellow. Okay. That doesn't necessarily mean the display server is not running or that the color map has all been turned to yellows or anything like that. Those are actually might be your initial hypothesis. All you really know, the screen is yellow. One of your assumptions of the question is in fact the screen yellow. What if you say lean in close to it and look at it and it's really red and green dots or striped and interleaved? Okay. That's an important thing to notice because if you set a bunch of breakpoints later on looking for yellow, you'll never actually find anybody setting the a screen pixel to yellow. So you want to really look at those, question those assumptions. Now for the hypotheses, let's say, why are your display widgets missing? Were they never drawn? Maybe they were drawn in yellow on yellow, so there you just can't see them. Maybe actually everything was drawn perfectly and a big yellow rectangle was drawn over top of them. And then maybe it's a hardware problem. Maybe there's red and green wires to the screen, they're just simply broken somehow. So the key thing here is to notice stuff. Red, green interleaved is something to notice. One of the things that happens with the modern programming is we do a lot of resiliency, defensive programming, modularity, all those good programming practices. One of the side effects from the debugging point of view is that the program may continue to run, may be struggling, but it is still running long after the real bug has been encountered. So some of this is really going to be that you're going to have some kind of advance hint that something is wrong. So, for instance, in a Linux boot up, Linux boot up is very chatty, has lots to say. Sometimes it has these ominous sounding warnings, but it goes on and everything runs. So one of the things to think about when looking at that kind of material is there something in there that's actually, is that your first inkling that something's going wrong? Especially you see something out of place. You've seen a log message you haven't seen before. You see a oddly colored pixel in the corner of the screen that you don't remember ever seeing before. There could be any number of things that normally you just kind of pass by. You don't really notice. It's down in the noise. But you have a bug out there somewhere, and it could be that the real bug is being given away by this little detail. Now, one of the nice things about when you get the moment of insight, it's very often a flash of realization. You understand what's going on. Everything is explained. It's very exciting. and we don't want to downplay that. It's like one of our rewards in the debugging process. But double check it. Okay. There's any number of times if you get the flash of realization, you jump to the code, and you've actually been led astray. It's not the real cause. You go through another round of fixing in the code, you go back to testing, and the bug's never gone away. It's just moved somewhere else. So we want to double check before actually jumping to change the code. One way to do that is simply to do a little test. Okay, you have what you believe to be your solution. Let the code run a little bit further, assuming it hasn't crashed. See if the behavior still fits. If the behavior starts to not fit what you're thinking, it's time to discard that hypothesis and go back and try something else. Another thing you can do, take the bad value. Say there's your flash of insight is that you've identified the single bad number incorrectly incomputed. You can manually change it, and this is actually something a debugger can do for you. Manually set the value to what its value should be, and then continue the program. See if it starts working correctly. If it starts working correctly, now you have a pretty good proof that that is in fact the real bug. But even so, be wary. Are you fixing a symptom, or have you actually gotten down to the real cause? And then finally, I wanted to say to tell others about the bug fix. It's not only it's sort of a personal reward to understand how to fix, but it's also valuable education to other people, like other people on your team, other people in the community. Tell them what the bug was, how you found it. If it's a bug you wrote yourself, maybe you want to downplay the part where you were foolish and wrote it caused the bug. But certainly it's valuable to everybody if you explain your debugging procedure. Maybe there's somebody later on that's going to fix their bug faster because they got some insight from your process. Okay, so that's some generalities. I'm going to jump a little bit into the specific strategies. First, we're going to talk about debugging on the host using printf, how to use the debugger, and talk about setting breakpoints, about how the evils of single-stepping, use of conditional breakpoints and other options, and data display options. So first, debugging on the host. Now, most people actually do this in practice. A lot of code starts out on the host. That's where it's initially developed, and it's a good thing because the host system has everything, right? It has its high-speed machine, high reliability, high flexibility. We've spent a lot of trouble to make the target, debugging on target, more effective and easier to do, but it doesn't really matter how fancy we make our tools. Debugging on the host is still the best way to go. Debugging, just the general debugging process is, like I said, it's faster and easier. It helps ensure that your code is processor independent. So if your target is ARM and you're sitting on a PC doing the work, that will help you factor out processor dependencies between, say, x86 and ARM. And so later on, if your target system is changed unexpectedly from ARM to an x86, your code will be ready to go. Important thing is that the algorithms are going to be the same. That means on the host, you can test and debug your edge cases. You have a nice, powerful system to check all the ones, especially the edge cases that are likely to crash your target system. You can run unit tests, regression tests, you can script things, you can really beat on the code in a way that's difficult to do in an embedded system where maybe the board's a prototype or you have limited time because you have to share it with half a dozen other developers. But on the host, you have all the time in the world. You can take care of all those things. You even have simulators available, and people use this. Android simulator is very well known. It essentially gives you a mock-up of the phone, and you can do the development. You're still sitting on the host, but you're working with a mock-up of the phone so that you actually get to see what the screen looks like. So the underlying reason for doing all this debugging on the host, it lets you pre-eliminate the generic code as a likely cause of bugs. So you have to spend less time worrying about whether your algorithm's correct, and you can spend more time focused on bugs that are due to difference between the host and the target systems. So debug on the host. Now for printing and logging, it's often said that only the amateurs use printf and the pros all use the debugger, but that's not really true. Actually, everybody uses printing and logging functions of various sort. And rather than try to promote this idea that somehow the debugger does everything for you, I want to say that printing is a good thing to do. And it has some advantages. You can adapt the print functions to the specifics of your code, format the output in a way that's most useful to that program. You can put it at the known locations that are already known ahead of time to be of interest. You can put conditionals on the print so that it only prints out when something is especially interesting or when something might be going wrong. These days, typically you'll have a pretty fast build and download cycle, much more so than it used to be, and that actually means if you actually put like two people on with a stopwatch side by side, it can actually be the case that changing the code to put in a printf and getting back to the same spot and to see what the printf output is can actually be just as fast as firing up the debugger and setting breakpoints. You do need an output channel. Now, in desperate cases, you can do things like memory buffers, so it's a printf, but it's a memory buffer, and you look at it with the debugger. In a couple desperate cases, and I've done this about twice, where you have just the LED, and you can make the LED blink in Morse code. It's not a real fast way to go, I can tell you. Many mature programs actually already have built-in logging of some sort, and so using it in an embedded context is very often it can be turned off just because it's an embedded context. So maybe your work is really just to figure out how to use the logging as with the target. The custom systems the logging systems are usually a custom design. People have invented various schemes that are more generic, but in general, they're going to be custom. The one thing to watch out for is that the logging system may have a lot of volume for other people's purpose, and so you end up with a haystack being built around the needle of the output you're really interested in. Again, not antagonistic to the debugger. And there's actually a kind of a handy little thing about some of these print and log function calls. They typically sit on separate lines, and they're actually very convenient places to put breakpoints. Okay, so the debugger. The debugger, it's your big gun, it's the gas chromatograph, it's the electron microscope, it's the NMR, whatever analogy you like to suit. It's the heavy-duty tool that you use when brain power and printf is not enough. It gives you a I say microscope level, it's not quite the same thing as saying microscopic, but it gives you a very low-level, fine-grained view of your program behavior. It has the advantage you don't have to modify your code. You can debug with the code in its final form on the target system. The debugger lets you look at everything in the address space. It cuts through all the abstraction layers. So the way it's coded, it just reaches in directly to the hardware and says, here's what memory looks like, here's what's in registers. And so so if you have high-level abstractions, it cuts through them, and sometimes that's a good thing. And because if the abstraction is wrong, it shows you what's going on underneath. The bad thing is it shows you all the minute implementation details that you may or may not be interested in. So it has its good and bad points that way. The debugger will have hundreds of commands, hundreds of options. Most of them you will never use. I've been using GDB for 25 years or so, and I've maybe gotten up to maybe half of its commands and features at this point. So there's a lot of stuff in there. A lot of the things are very special purpose. They're coded up for somebody and left in the debugger on the off chance that maybe somebody else will find them useful later. So it's interesting to thumb through the manual, the debugger manual, to see what's available, but really a lot of that stuff is kind of obscure, and if you're not seeing an obvious use for it, maybe because there isn't one. And then finally, debugger is, despite the name, not the magical bug finder. It is a fire hose of additional information that you can make use of, but you still have to use that information to decide what the bug is. Okay, so we'll talk a little bit about how to use it effectively. First thing, program is big, location of the bug is small. So really the game with the debugger is to try and narrow it down and to use the various options and tools to narrow down the location of the program as tightly as possible and as quickly as possible. So basically the thing to do is make a guess based on the location of the bug. If you had to guess, and guess ahead of where the bug occurs, but not too far ahead, set a breakpoint and run to it, and then look around. If it's not interesting, make another guess, set another breakpoint. Breakpoints are pretty cheap. They have no effect on the program execution once the program is running. They're implemented in terms of trap instructions, but they lie dormant until you actually execute that code. So there's really no penalty for having lots of breakpoints. Conversely, single stepping is not as useful a technique. It's easy to do. You can just start single stepping, watch the little counter go up and down, and so forth. But it really it kind of sucks up a lot of time to do this. And at each single step, you're looking at the variable, saying, well, is that variable okay? Is it not okay? And then you spend time thinking about, well, what the manual calculation is effectively for that variable. But so what happens then is you can end up soaking up a lot of time and not have much to show for it. So I generally have a rule that says after you've done a couple dozen single steps, you're going nowhere fast, just simply stop single stepping, pick another breakpoint, set it further down in the same code if you still believe that that's the module that's at fault. Pick a different module, do a new hypothesis, whatever, but don't spend a lot of time on single stepping. If you do find yourself single stepping a lot, and it seems to make sense, do make use of the step over option so as to get past function calls. If you step into a function without intending to, and you know it's not an interesting function, you can also, there is a step out or finish command that will get you back out of the function, get you back to the main single stepping. So it's really the name of the game here is about how to converge faster. The nice thing is if binary search works well and it converges quickly. Suppose you have 1,000,000 lines of straight line code. It only takes 20 iterations in binary search to get to a specific line. Now the flip side of that is you do have to know what you're looking for. So binary search, because you have a condition and it says true or false. Let's say take the thinking of the yellow pixel example. You want to find something that says yellow pixel. Is my value equal to yellow now, or is it not yellow? If you have something like, well, I'm looking for a memory map a color map that might have yellow in it, but I'm not sure. Binary search doesn't work because you'll sit at a code and you say, well, is it already bad, or maybe kind of looks bad, maybe not, I'm not sure. But if you randomly pick one side of your search and you have a vague condition you're working with, then you've just totally messed up your binary search process. One of the other things to watch out with that kind of thing is you converge partway down get partway down your binary search, and you say, aha, I know what the problem is, and then you kind of continue doing the binary search, but you've changed your test condition. If you change the test condition that you're searching for, you really need to start back at the beginning, because if you've changed the condition, you don't know which half of the search you're on anymore. So it's better to be disciplined, and instead of trying to optimize a little bit by changing condition in midstream, start all over. Now, loops make a problem for this whole thing. A million lines of straight line code is great, but the loops actually make it worse. It's really a lot more than a million lines of code when you count the looping around. So we have a couple options that help us, that are most useful in helping us get through loops. First, we have the ignore option. And the ignore option says skip the next n hits of the breakpoint. And n is the number you have to choose ahead of time. So what you do is you guess at an n that will get close, and then decrement it. If you have to do a couple extra breakpoint steps to get to the right location, that's much better than having overshot. So just pick a number, decrement, and work with that. Another option you have is the breakpoint conditional. And what this is an expression written in the vocabulary of your program using your own variable. And the breakpoint will only stop if the expression is true. If you're about it and you choose the expression wisely, you can set it up so that the breakpoint will stop exactly at the line with exactly the variables you want if you've hit it in one. So instead of spending half the morning looping around with breakpoint hits, you've gotten there right away. Okay, so now I'm going to do a little switch over to a video where we show this happening in CodeBench. So undo the screen share here, and then we'll screen share. Okay, and if we're lucky, we have a screenshot. And basically, I've set this up as a video to avoid the demo misbehavior, defeating Murphy's Law. So what we have here is a small program that is just increments, does some arithmetic on a variable, and does some printfs in our style. And I'm actually running this native so that to eliminate that kind of difficulty. And so what I'm going to do is demonstrate the ignore counts and the conditional breakpoints. So the first thing we'll do is to run the program. And we're always optimistic. We want to run it straight through, and does its thing. And we did set it up in debug mode, so release that to pessimistic. We run the program straight through with everything set, and big var comes out to be a negative number, which is not what we expected. So we set a breakpoint at the calculation for big var. And we go back, restart the program. Now, big var looks good so far. Now, in this case, I'm doing some single steps. I could as easily just do repeated runs to the breakpoint. And I'm seeing I'm going nowhere fast. The big var is getting bigger and bigger. And it's not obvious where the negative stuff is coming from. So now what I'm going to do is set up a condition, just simply big var less than 0. Set that up. And then I do a resume. And boom, right away shows me big var being negative. Now, the good news is, yes, I have a negative value. The bad news is I don't really know quite why it's negative. Now, the first thing is that we should, in the category of noticing, we notice that big var is around 2 billion. And in a 32-bit system, a value around 2 billion should ring alarm bells because that means you're dangerously close to wrapping around. But I'm going to take the value of counter, and I'm going to use that as my ignore count because I can see I'm counting from 0 to 100. And so now I'm going to start all over again. And now it comes to a stop. And now big var is still negative, but now it's a big positive number. And so then I single step, and boom, there's my flash of insight. I've taken a big number, I multiplied it by 2, turned into a big negative number. Well, duh. I've overflowed a 32-bit value, and then I'm done. I figure out whether to change big var to a 64-bit value or change my algorithm to declare it unsigned if I want to go to 4 billion, whatever. Okay, so that's the example of conditionals and ignore counts. Turn off the screen share here, and we'll go back to slides. Okay, moving on. Okay, now we're going to talk about some trickery. And trickery is basically a rogues gallery of the usual suspects. And I'm going to talk about several classes. I'm going to talk about wild rights, program is not what you think, hardware bugs, sounds like Jeopardy categories, races, and then Heisenbugs. These are all especially interesting for embedded software because embedded systems are unusually susceptible to these. Safeguards in the host systems are not present, and the embedded system by its nature tends to be optimized for the end user, not for the developer. So all these kind of problems can happen on a host in a host debugging situation, but embedded they're especially nasty. So first, wild rights. It's the basic fact of C and C++. It's why we love the languages so much. They can write anything anywhere. It means you can write on the stack, not necessarily on the part of the stack that you think you're writing on, but elsewhere. Like you can write on other local variables. You can write on the function arguments. It is even worse. You can write on the return addresses or the registers that were saved on the stack. This can be very confusing because you think that the debugger is giving you an accurate view of things, but you've scribbled on the stack. The debugger doesn't have any kind of magical way of knowing that these values have been scribbled on. Scribbling on global variables. You get a wild pointer running and you can scribble on all the global variables one after another. They tend to be allocated at consecutive locations in memory. You can scribble on the space used by the library. One especially evil thing that happens is you can scribble on your malloc blockchain, which is how the malloc library keeps track of memory that's been allocated and what to hand out next. But if you have a wild pointer writes over all the blockchain, everything that's allocated has been forgotten about. And if you're lucky, if your next allocation fails, because then you have a
All right, Stan, I think we're back live here.
Okay.
So you can pick up your presentation.
Okay, let me pop up screen share. And all right, so in theory, we're back in action, and the little crash there perfectly illustrates my point about wild rights, because despite all the fanciness of fancy talk of fancy languages these days, still a lot of the infrastructure of this is built with C and C++ code, and it does exactly this sort of thing. Anyway, so the next thing that can happen that bad for embedded guys, if you don't have an MMU, you can do wild rights on the program itself, and that's be quite an interesting situation. Finally, you can have them on the operating system. So there's lots of bad things that can happen, and there's a variety of techniques. Binary search is one of those techniques that works really well. You can do watch points, and I don't have time in this one to go over the details of watch points, but that's the kind of thing they're very useful for. And then general paranoia, that if things don't look like they're adding up or making sense, that's wild rights is quite often an explanation for that. So we have a little example where I put together another a program that actually does the wild writing, and then to show what happens in the code bench for that. And we'll And so what we have here is a little program called wild, and basically we have a global variable and an index, and we're just going to start scribbling into memory, starting at the location address of a local variable, and then we're just going to work our way up the stack and see what happens. So let's give a little illustration of what the program does. Doesn't really do very much. As a loop, it's going to write 100 words of numbers, different numbers, and it's called by a couple layers of subroutine. So we have a little bit of stack to look at, see what happens to it. So we run the program, and unsurprisingly, bad stuff happens. Now, in terms of noticing details, the fact that I have a stack trace in which each element of the stack is consecutive integers is actually would be a real giveaway. Something very bad has happened. Not only something very bad happened, but those numbers are coming from something that does incrementing. So if you're really paying close attention, that actually tells you enough to gives you a pretty good clue about where the bug really is. Well, we're going to pretend that it's mysterious and set a breakpoint, and then try running forward and seeing how this develops step by step. So we set a breakpoint at the wild right, and the first stop, everything looks okay. Arguments are what we expect to be. The local variable is what we expect it to be. We do a resume, and now the variable's been set to 0. It's what we expect because we just set it there. If it was a more complicated program, the fact that a variable is changed to 0 without having been set to any value by any code that you can see, that's a giveaway that something is about to go wrong. Note the stack tray still looks relatively normal at this point. Okay, now we've done another one, and now, well, the variables haven't changed, but look at the stack trace. The main has disappeared from the stack, and it's kind of an obscure explanation as to why, but that should be another single step again. Okay, now things are getting really funky. We're trashing the stack. The stack is getting more and more trashed. Although we haven't actually crashed at this point, but we notice the arguments to the function are now changing, and then we're getting nonsense functions, libc start, main start, and so forth. Things that you would not normally expect to see in the stack trace. So this shows just how bad things are getting. So anyway, so the gist of this is to really show you that the wild writes that they can be very confusing. They can appear to be completely different bugs, but you're getting a situation where they don't make any sense at all, and that's a good sense that something else is happening. Okay, so we'll turn that off. Go back to slides. Yeah, actually, an interesting tidbit on that is that it actually took a while to write a program that actually scribbled on things in a relatively controlled way. I had the initial version of that had the pointer and wild as local variables, and they instantly wrote upon themselves, and so then the program went weird, but not in a predictable way. Okay, so another kind of trickiness is the program is not what you think it is. For instance, this is something that happens a lot with embedded. The code that's actually on the target is not the code you think it is. Upload failed, download failed, JTagging failed. There's 2 copies of the code in memory and you're at the other one. There's a lot of things like that can go on. So if there's some reason to suspect, like for instance, one of the things that will happen is that the code will stop in between lines. and that's like a hint that maybe the code on the target is not what you think it is. Is the source code for some other version. Again, so you got confused in the compile process, you uploaded an ancient version of the code, the code matches, but it doesn't match the source. Macro expansion is, can produce something radically different. And this is actually one way in which the host and target can change, so that the host version of the software has a sensible macro expansion and the target version has some other macro expansion that you didn't know about. So you can end up things like the code's missing, there's dead code, integer sizes change. Especially these days when you have a 32-bit target and a 64-bit host, the host may work just fine because it's using 64-bit numbers and the target's not because it's using 32. Optimization is, of course, a popular way to have the final code be different from the original code. Actual compiler optimization bugs are rare, though. Compiler testing goes through a lot of code, weird code, mostly weirder than yours, most likely. But optimization does expose latent bugs in your code. Dependencies on evaluation order, uninitialized values, and so forth. Hardware bugs. Hardware bugs are pretty rare. The board bugs, somewhat rare, maybe more rare if you are doing a prototype that came from the lab down the hall. Chip bugs, you're just not going to see those very often. I've seen maybe 1 or 2 chip bugs in my career, honest to God chip bugs of the not publicized sort, not counting Pentium F div bugs or things like that, but other ones that were honest to God chip bugs, and there was quite a bit of work actually to get to the point of even proving that it was a chip bug and not something in somebody's code. So in general they do happen, but that is going to be your absolute last resort. Now races are more common, and they're kind of an ugly problem. They're timing dependent misbehavior. Operating system, they really come in when you have threads, multiple threads, and or hardware devices running concurrently with your CPU. One of the things to keep in mind, the OS schedule can keep a thread suspended for a lot longer than you think. Just because you imagine that it's being fair and giving everybody an equal amount of time, that's not necessarily the case. The OS could have, for some reason, decided to starve one of your threads for quite a long time. In fact, you could have had a wild write that scribbled into the OS scheduler, and the reason it's leaving your thread suspended is because its own state has been corrupted. With multiple cores, it gets even worse because the threads can run genuinely simultaneously, and they can be interleaved in their execution at the instruction level. So all that locking and stuff, you really have to get serious about it. Now to debug it, there is a non-stop mode that's available, and it is possible to control threads execution individually, and I won't go into that because we're getting pretty close to our time here. And then finally, Heisenbugs. Now Heisenbugs are things where the debugger itself can affect the execution, and the debugger is a program, does change program behavior, although it does its best to stay out of the way. But a breakpoints, the single stepping, they affect program timing, they change the winners and losers in races. Sending bytes to and from the host to the target, that pushes bytes in the I/O channels that might not have been there. Debugger grabs signals. Debugger does breakpoints with trap instructions, so it's modifying your program. It's installing trap instructions, removing them, reinstalling them. And of course, you're going to have peripheral registers that modify their values based on being written. So these are all ways in which the program works fine without the debugger or has a different bug when you run with the debugger. So it's something to be aware of. So we have a quote from Sherlock Holmes, famous computer programmer: "When you have eliminated the impossible, whatever remains, however improbable, must be the truth." And this comes up just a lot. You say, I know I haven't changed my program. Well, you did change your program because you re-uploaded it. So maybe you didn't re-upload what you had. So You use your problem-solving process. You watch out for your assumptions. You notice the details. We have our basic strategies of using the host, using printf, using a debugger. Breakpoints are more effective than single-stepping, and at all times be alert for trickery. So that's the formal part of the presentation. We have a URL, point you to Mentor Embedded and Codebench and all the good stuff underneath. And then for GDB has its own separate website that's managed by the GDB community and has a lot more in-depth stuff. So turn off the screen share there. And then anybody's got any questions, ready to answer.
So Stan, it looks like Hans Bayer asked, have we ever heard of Ivory, which is an embedded DSL in Haskell which compiles to C and makes wild writes impossible?
Ivory is not something familiar with to me. Certainly that's it's almost like a holy grail of low-level system programming, is to come up with a system that eliminates the possibility of memory corruption, but still lets you have low-level programs. And there's no system, I say, that really is good enough to be a silver bullet. Another example that comes to mind is various garbage collections schemes for C code. People have actually had some luck with those. I think all of those, using them embedded is probably going to be a challenge, because you'll essentially need a way to still have hardware access for embedded systems and yet have the safety at the same time. They're essentially contradictory goals. But certainly it's worthwhile to keep an eye out to see, do you really need low-level language? Do you need to say get the maximum out of the hardware and expose yourself to the wild write problem?
One other comment, Stan, Dennis Jump earlier in your presentation towards the beginning had a comment that just said, I find explaining the bug to someone else long before telling someone about the fix is a good path to clarity, insight, and explanation, even though the person you are telling has no idea what you are talking about.
Yeah, and I think that's a very good point. That's in the category of stating the problem. Actually having to put words to it and state it out loud is a very useful way to make sure you actually have stated the problem, as opposed to the jumble of thoughts running around in your head. If you actually have to string it into words and say, this is what the problem is, that is a useful way to do it. And explaining it to somebody else is one way to force yourself to actually make a coherent statement out of the problem.
Excellent. Well, thanks very much, Dan. It looks like that is all the questions and comments that we have for now. So, folks who are watching, thanks for joining us. Thanks for bearing with our YouTube bonk that we had. It looks like we've got 2 different YouTube videos that we'll need to combine and post on this page, which we will get done in the next day or so. If anyone has any questions post-event, please feel free to post them on our chat section below this live video, and we'll come back and check it a few times in the next week or so to see if there are any other questions to address. And in the meantime, thanks for joining. Stan, any last words? Oh,
I was just going to say, if you all like this, because I really had to kind of cut it off at a relatively basic level for this. If you all like this kind of talk, I can do future talks that go into more depth on some of the advanced technologies, watch points, trace points, non-stop debugging, and so forth. There's quite a lot of interesting material there, and I'd be happy to go into it in depth.
Excellent. Well, we've got a few more of these planned in the future, so we'll get that on the schedule, Stan. So thanks again, everyone. Please feel free to post any questions, and thanks for joining. Have a good day.
Thanks, everybody.